Okay, hi folks. Maybe we should just get started. I don't know, Rick, if you're around, like, should I just start? Is that fine? Okay, let's just get started, folks. It's 11:01. So, hey everybody. I'm Karthik Ranganathan. I'm one of the co-founders and the CTO of Yugabyte, and I'm here to talk about how we extended PostgreSQL to a Google Spanner architecture, right, which is cloud native. So, without further ado, let's just jump right in. So one of the things we do at YugabyteDB here is to build a cloud-native database. That's a distributed SQL database, right? And the first thing we did when we started to build and design the database is how would we design the perfect distributed SQL database? The two things we put next to each other are the fact that, firstly, PostgreSQL is more popular than any other database in terms of adoption. It's the fastest growing database, even compared to Mongo or anything else. And Google Spanner is a truly horizontally scalable and a strongly consistent relational database that is cloud native, right? However, if you look at the two sides, the PostgreSQL is not cloud native in the sense it cannot do scale, high availability in spite of failures, geographic distribution, distributed transactions, etc. And Google Spanner does not have all the RDBMS feature set and the goodness that PostgreSQL has, right? So we said putting these two together is probably the best way to build the perfect distributed SQL database, and that's what we undertook, right? So this talk is really about how we went about doing that. So if you compare the two, the query layer and the SQL features that you get as a part of PostgreSQL, they're actually really well understood, well adopted, well known, and really, really advanced, right? And Google Spanner actually misses a lot of these. It has a very basic feature set, and it's a completely new flavor of SQL, right? So you're missing things like, for example, triggers or stored procedures or partial indexes or a whole bunch of long list of features, right? Now, if you look at what Google Spanner has done, though, it has high availability, horizontal scale, and distributed transactions, right? It's capable of doing all of that, which is great. And Google Spanner does synchronous replication, while Postgres and most of the RDBMSs do asynchronous replication. The first set, the query and feature set, are extremely critical for adoption and for building good applications, right? And the next set of features are generally really good for cloud native development, right? So with YugabyteDB, which is a completely open source database, just like PostgreSQL, we said, how about we combine the best of these two worlds, right? Like we combine the best of the PostgreSQL in terms of its feature set. We'll get the best of horizontal scale, HA, and distributed transactions like Spanner, and we'll retain both synchronous and asynchronous replication so that you're able to build whatever kind of relational or transactional application, but in a cloud-native fashion, right? So this talk, the rest of this talk, is about how we did this in about 7 steps, right? Like obviously we're going to make it sound very simple, but it's been 5 years and it's taken a lot of work. So these steps, while they're a broad set of steps, are actually quite detailed in themselves. Right? Okay, so step number 1, the first question we asked ourselves is, what features should the new database support? And should we rebuild this database from scratch at the query layer so that it works really well with the distributed substrate? Or should we reuse the PostgreSQL code base and just support everything that Postgres had? We said, let's rebuild it, right? But what do we want to reach? Because rebuilding is always quite easy, or so we thought. We said, let's start there. But we wanted to support everything in Postgres, the basic data types, the queries, built-in functions, all kinds of joins, recursive queries, all of your advanced features, your extensions, foreign data wrappers, the works, right? So people should not get too much of a surprise if they move from Postgres to Yugabyte. And most of these today are supported in YugabyteDB, right? So how would we do that? So we first thought, okay, reusing is actually great, but the Postgres code base is really complex and it does a whole bunch of things. And it's built for a single node, and getting a single node database, removing the lower part and actually making it work on a distributed substrate is actually unknown if it will work or not, right? But its reuse is actually quite risky. So we said, let's try to rewrite it, right? But then when we said, like, let's just connect to a Postgres database and issue the /d command and look at what does it do, which actually lists the tables, and say, what kind of a query does this command actually issue under the hood, right? And that's when we got the rude shock that it does a really complicated query, which has pretty much everything in there. It has aliasing, it has a case, and if then else, as a case clause. It has built-in functions, where clause, all kinds of operators, sort by, joins, everything, right? So we said, hey, if you're able to just support this one command, which lists tables, will be most of the way to supporting a lot of the relational features in itself, right? And it kind of became apparent that at this stage that, given the complexity of how people use something like Postgres, it's going to be very difficult for us to rebuild this from scratch and make it work exactly like Postgres. So we concluded it's impossible to get this level of compatibility without reusing the code, right? And this shows that the fact that we had to take the risk of figuring out how to get Postgres to actually distribute early on. But most of the other distributed SQL databases like Google Spanner or any of the others don't do that. They try to build the query layer from ground up. And building these features is really hard. It takes a lot of time. The maturity and the functional spec of these features is hard. The testing is hard, and so on and so forth. Right? So now that we had decided we were going to reuse the Postgres code base, the second thing that we said was, how should the high-level architecture look, right? And what were the choices here? We said we wanted a two-step architecture layer. If you're reusing Postgres, obviously we could not use the lower half of Postgres, which writes to a disk. So we said the upper half is literally Postgres, and we will reuse the code, but the lower half has to be Spanner inspired because we said we wanted to put Spanner underneath, right? So it's got to have no dependency on any specialized hardware. Spanner actually depends on atomic clocks, which were not okay for us. And it had to be a Spanner inspired store. And we said a document store is probably the best because we want the flexibility of storing data the way we want it at the lower half. Right? So the way we did this is as follows. If we took a look at the Postgres layer and said, let's logically separate the Postgres layer into a query layer or the language layer above and the storage layer below, right? The storage layer includes things like the wall writer or the background flusher or vacuuming or a whole bunch of other utilities that do stuff on the disk, right? We said we've got to separate out the lower half and actually run it on a distributed substrate. So that was step one, where you're able to take the query layer that sits on any node and have it talk to the storage layer on any other node, right? Therefore, giving you the illusion of being able to talk to any Postgres layer above and it truly talking to the distributed substrate below, right? Once we achieve that, the problem in this diagram, though, is the query layer still reads all the data from all of the storage layers and brings it to the node that handles the transaction on top. Right? So we said that would not perform really well. So the next step was to break down certain sub-operations inside a SQL execution plan and start pushing them closer to the storage. So you don't have to move storage to where the execution happens. You can move the query execution to where the storage lives, right? So that was step two, figuring out what kind of subtrees and plans can be pushed down. Right? And step three is actually to rewrite the query plan itself to take into account things like table statistics and location and the network cost, and how do you rewrite the query plan to work better on a distributed database as opposed to a single node database, so that you can actually push down more and more of whatever operations you can do. Right. So by definition, these three steps are always running, right? We keep doing more and more. And the level of maturity is the first step, which is getting Postgres to run, is probably the most mature. And the third step is the least, but this is just something that we do over and over again. Okay, so given that we had a strategy now, we had a three-step process of first getting the Postgres layer to increasingly run and work on a distributed substrate, and then increasingly push down, and then tweak the query plan to make it work better. Like now that we had that, we said, okay, let's figure out how to map PostgreSQL internals to a distributed storage layer. So how do we do that? The first thing was when we looked real deep at how, not real deep, but even at a high level at how the PostgreSQL architecture works. We found that the SQL application actually talks to Postmaster, which is responsible for authentication, authorization, and all of that. And it does a rewriter, a planner, executor, optimizer, all of this stuff, which then goes to the disk utilities, which talk to the local disk. Right? We obviously wanted to reuse the query layer of Postgres, which is the upper half, and replace the lower half with a distributed storage layer called .db, right, inside YugabyteDB. So that involved actually making some changes to the planner, the executor, and the optimizer. right? And these changes would actually enable the upper half to talk to any node below, right? So that means we can simplify the overall deployment process of this database to say, we now converted the upper half to a stateless upper half. You can talk to it from any node, and it would talk to the right lower half, right? So that means your SQL application can now connect to any node, and you can add and remove nodes at any time you want, right? And you can survive the failure of a node because you can always read from a different node, and the lower half is fault tolerant and replicated, so it can survive failures in a highly available manner. And the upper half is stateless, so simply connect to a live node and you can get back your data. So you are able to both scale the database as well as tolerate failures, right? So this was the high-level approach to how we'd go about doing it. Okay, so we said theoretically all of this should allow us to scale the database and to be resilient, right? So now let's look at how we achieve that scale, right? So in order to achieve that scale, like we have to be able to distribute, like let's take a single table. We should be able to distribute the data for a single table across multiple nodes, right? Like that's really the most critical property that allows you to scale the database across multiple nodes. So, I mean, let's take 3 nodes, and you can have these 3 nodes either as just living inside a single, location, or 3 different fault domains. So in multiple zones inside a region, or multiple regions, or even different clouds. It doesn't matter. So you have 3 nodes that are in 3 different fault domains and connected with a network, right? Now, how do you distribute data across these 3 nodes? That's the fundamental question for a single table. So we took a logical table view, and we said, like, we need to split up the rows of this table into groups or subsets of rows, and we call each of this a tablet, right? So take a table and split it up into many groups of rows, each called a tablet. So we don't cut a row halfway. We keep just groups of rows, right? And this type of sharding is transparent to the user, right? So once we do that, we now have a table that is now comprised of many different row groups, and we're able to distribute these row groups across the different nodes, right? So this scheme called sharding is transparently allows you to spread the data of a table across nodes. And of course, there's other concerns like how do you make sure that a table is evenly distributed across nodes and there's no skew, right? So there's a notion of how do you keep the load balancing across nodes even. And we're just using an example of 6 tablets in this diagram so that it makes it simple to view with different colors, each representing a different group of rows. But in the real world deployment, there's going to be many, many tablets per node, right? So and there's really no restriction on how many. And in practical scenarios, you could have 10, 20, 30 tablets per node, depending on the size of the table and what we're trying to achieve. Note that of all the rows of the table, each row belongs uniquely to one tablet, right? And all of the tablets of a table together should give you back all the rows in the table. So in reality, there's no row that's lost and there's no row that's owned by 2 tablets. So there's got this property that one row is owned by 1 tablet. Okay, so now how does horizontal scalability work in this kind of a scenario, right? You're able to take this 3-node setup with a bunch of tablets, and if you add more nodes, you can simply distribute the tablets to more and more nodes, right? So as long as you have enough tablets, you'll be able to spread it across a lot of nodes. And even if you don't have enough tablets, you can dynamically split these tablets into smaller subgroups of rows and split them across more and more nodes, right? So that means now we've solved the property, we've solved the requirement for scaling a single table, where you can say, I can increase or decrease the number of nodes that a table's data is spread onto. Okay, so now that we looked at scale, let's look at how you achieve high availability and resilience, right? So whether you're doing, for example, a software upgrade, or whether you have a node that dies or a zone that goes out, how do you ensure that your database can still stay up and serve data, right? That's really what we're trying to answer. So because in the cloud, when you try to get machines, failures happen all the time, and software upgrades happen all the time, and you don't want to take a downtime for either of these. Right? So the way this works is like we talked about how we split a table into tablets, right? And we spread these tablets across nodes. Now, you'd not be able to survive a failure if you don't have the copy of the data on other nodes, right? If you have exactly one copy of the data in the cluster and that node goes down, you're not going to be able to serve that data. So we said we need to replicate this data, but replicate it in such a way that even in spite of failures, the cluster can still serve that data with no data loss, right? With absolute consistency. So the way you do this is using the Raft consensus algorithm, which actually ensures this property. So you have a tablet that's now replicated across 3 nodes using the Raft consensus algorithm. Raft actually makes one of the nodes a leader, and this can dynamically change over time. However, the Raft leader takes all the reads and writes and replicates it across the 3 nodes and waits for a majority of them to persist the data before going to the next read, next write, right? And on a failure, a new node can quickly be elected the leader. Right? So again, I'm not going into the details of how Raft works, but the point is every tablet is replicated using Raft. And so if you now look at our 6-tablet setup, this is how it starts looking. So those tablets that we had on the various different nodes, they now have replicas of in the other fault domains, in the other zones or regions or clouds, so that you're able to survive a failure and automatically serve out of a different location. Now, if you look at the reads or writes, the read or write for a particular row will always go to the tablet leader that Raft elects, and the tablet leader will figure out if it's a write, how to replicate it to its followers. And if it's a read, it can just serve it straight up from the leader. Right? But note that splitting up the table into tablets and distributing these tablets across, it's also important if you want to utilize all the nodes to make sure that the tablet leaders and followers are balanced across the nodes. So in this example, you see that node 1 has 2 of the tablet leaders, node 2 has another 2, and node 3 has yet another 2, right? So these disks with solid boundaries are tablet leaders and dotted boundaries are followers. So you find 1 leader and 2 followers for a disk of every color, right? So, so that means that what you get in this kind of a scenario is the tablet leaders are spread across nodes, and thereby we're able to utilize all of the nodes evenly. Okay, now how do you scale in this kind of a scenario? This is how it starts looking. You just spread the tablet leaders and followers across the different nodes. And this is an example of a 6-tablet setup. And as I said, you probably have a lot more tablets in practice. You get a read to a tablet leader, and it figures out which node, where to replicate for. If you're doing a read, it serves it right away. If you're doing an update, it figures out how to replicate data. Right? If a node fails, right? So we wanted to do high availability on planned and unplanned failures. So if it's an unplanned failure, let's say the node fails, then the Raft algorithm elects a new leader. And if it's a multi-zone setup, it can get re-elected in about 3 seconds, right? So if a node fails, for this tablet leader, which was handling reads and writes, you'd have an outage for 3 seconds. And in 3 seconds, one of the other tablet leaders that are a hot standby or an active standby would actually take over the reads and writes. If it's a tablet follower, you're not really impacted, right? Because somebody else is the leader, and this leader is going to be serving the reads and writes, and you're going to be totally fine. So the database is unavailable for reads and writes for this one tablet for the window of the failover, which is about 3 seconds, right? And the amount of data lost is actually 0. So in this case, because your new leader, as soon as it dies, would not be able to replicate or take more writes, and the new leader would be able to seamlessly transition from there. Now, let's say the node is down for a while, right? Like it's not coming back up anytime soon. So you have a flag to control what a while means, like if it's down for a while. But after about 15 minutes, that data gets re-replicated onto new nodes. So you find that in the diagram before, you had this yellow and the purple color up on node number 4. And now you have the yellow and the purple replicated to other nodes in the same zone, right? And this happens just automatically. You don't have to do anything. And once the node 4 comes back, the database will actually transfer back a couple of tablets back to node 4 because you want the system to be balanced, right? In terms of the number of leaders and followers and the number of tablets. If you lose an entire zone, it's the same thing. Like what you lost in effect is 2 leaders and all of the followers. Losing a follower doesn't matter. You don't lose anything. Losing a leader simply means that in a few seconds you'd have the leader do a failover and you'd be fine, right? Like in about 3 seconds you'll have the database completely serving, the database cluster serving your queries, and it doesn't matter that you just lost an entire zone or region or whatever it is. So the way to characterize this is in a multi-zone setup, your RPO is 0 on a node loss or a zone loss, and your failover happens in 3 seconds for a subset of the data. Most of your data is still fine. And your RTO, which is time to recover, is about 3 seconds. Right? Okay, so we looked at scale. We looked at availability. Now let's look at how we actually do transactions. Right? Okay, so it's easy enough to figure out how to do a single node transaction because you simply go to a RAF group and you make the update, right? That RAF already takes care. But what do you do with it for a transaction that updates multiple keys or rows, right? Let's say your transaction is begin transaction and you want to update key 1, key 2, and commit. So the problem here is key 1 and key 2 may belong to different shards or tablets, and each of them are being replicated on different RAF groups on completely different nodes, right? So it starts looking like this. Your update for key 1 goes to one RAF group, and your update for key 2 goes to another RAF group, and they're going to be on completely different nodes. However, because it's a single transaction, you need the updates to get written and made visible at the same time, right? And you need these nodes that have nothing to do with each other to agree on time, and you need to do so without an atomic clock. There's really nothing synchronizing time in a very fine-grained manner across these nodes, right? Google Spanner does this with an atomic clock service called TrueTime. Now, we wanted to make sure it didn't have any, it didn't have any dependency on specific kinds of hardware. Right? You should be able to run this anywhere, the YugabyteDB anywhere, right? So how do you do that? The way Yugabyte solves this problem, and what we did was to bring together a physical clock and a logical clock. The problem with a physical clock with NTP synchronization is that the clocks can drift by 100 to 250 milliseconds, right? And so that means you wouldn't be able to tell if two clocks are running at the same time based on the timestamp that the clock says, because they can be about 100 to 250 milliseconds apart. And so if you go to the first node and you write something, and you go to the second node and you write, and you read the same thing, you may or may not see it if the node times are not synchronized for another 250 milliseconds. Google Spanner, in Google Spanner, that this time is 7 milliseconds because their atomic clocks can give you a bound to say your time drift is the time skew between nodes is going to be no more than 7 milliseconds, but we don't have that luxury, right? So the way we deal with this is we say, okay, let the NTP actually synchronize time coarsely for 100 to 250 millisecond window, but we're going to add to that time a logical component where we track, all the correlated updates, and we keep exchanging what is called a hybrid logical clock, where it's a part physical and part vector or logical clock. And we say, like, when two nodes exchange this, they're going to keep bumping up their physical time, and they're going to rely on this hybrid logical time, which does time synchronization across the set of nodes in the cluster. And this synchronization happens for every RPC exchange, so any heartbeat, any raft update, leader election, etc., etc. So probabilistically, this system converges pretty quickly, right? And so we're able to actually get time normalization across the cluster. Okay, so now that we have time reasonably normalized across cluster using the hybrid logical clock, we said distributed transactions should be highly scalable. So we based it on a Google Spanner-like design, which uses a two-phase commit and with hybrid logical clocks for time sync. It gives you better scalability and is better for multi-region deployments, because our assumptions are that global deployments will get very popular. So multi-zone, multi-region, and all kinds of replications are going to get really popular. And clock synchronization in the cloud will get better over time, which it already is getting better because Amazon, Azure, everybody offers a time sync service. And this does not require any customized hardware in the form of atomic clocks. So the way this works is any node in the cluster can actually become the transaction coordinator. So there's really no single point of failure or bottleneck. And the minute you receive a transaction, you need to track the status of a transaction, because the transaction can make updates across multiple RAF groups across different nodes, right? So you do that using a global transaction status table, right? And all of the active transactions go there. Whenever you create a transaction, it gets created in a pending mode, right? So that means the transaction is currently in progress. And a transaction can go from pending to either committed if it successfully is committing, or aborted if it fails for some reason, right? So it's just two states that it can go to. And all of the reads can only get served for transactions that are committed. Right? So aborted is ignored, and pending means you cannot serve it because something is going on. So those are the stakes of the transaction. Now let's look at like the isolation levels, and then we'll look at how an actual transaction happens. Right? So the two isolation levels that YugabyteDB supports are serializable and snapshot. Right? Serializable isolation level detects read-write conflicts as well as write-write conflicts, and it maps to the serializable isolation level in Postgres. The snapshot only detects write-write conflicts and maps to repeatable read committed, and read uncommitted in Postgres. I mean, snapshot actually maps to repeatable read, but we map all of the lower levels to snapshot isolation because as a transactional database, we don't believe in an isolation level that's lower than repeatable read. Right? Okay, so distributed transactions write path works as follows, right? This is how the transactional write path works. So let's say, and tablet servers here are just nodes, right? So let's say that the client issues a transaction, like the example we took, where the begin transaction set key 1 to value 1, or like insert key 1 comma value 1, key 2 comma value 2, and these two rows belong to different nodes. Right? So the transaction manager actually first writes this to a status record on a transaction status table, and this write is replicated using raft across a set of nodes, right? And this just says, okay, I'm starting a transaction, it's in the pending state, and wait for me to come back and flip its state. The next thing it does is it's going to write provisional records to other nodes that actually form the raft group for the rows that are being inserted. So the key 1 tablet leader actually gets the update for the key 1 equals value 1. And it's written as a provisional record. A provisional record is kind of like a persistent lock in some sense, right? So you write the key and the value, and you say it's a part of a transaction that's in progress, but you don't assign it a timestamp at this point. You just say, look, just take this write and go ahead and see if you can lock that row for me and don't let anybody else write it. Now, somebody else, so two things could happen. When you came to write this provisional record, somebody else could already have written a provisional record. So you detect a conflict, you run your conflict resolution rules. Sometimes it's okay to go ahead, sometimes it's not, right? When it's not, YugabyteDB today is an optimistic concurrency control engine. So it's going to either abort the current transaction or the transaction that was already written based on some priorities and some details. But anyways, so it's going to fail one of the transactions if it conflicts. And if it doesn't conflict, it's going to go ahead and complete all of the provisional writes. Now, if you get a read that comes in, the same thing happens. The read detects a provisional record and says, look, there's a part of a transaction. Let me go check the status tablet leader. The status tablet table is going to say, this transaction is pending, in which case you have to run your conflict resolution. It could say this transaction is aborted, in which case you ignore it. And it could say this transaction is committed, in which case you read the timestamp from the status table and you use that row as if it was committed at the timestamp that is mentioned in the status table. Now, let's assume you were able to perform all of the provisional writes. Then the next thing you do is you go back to the status table and you say, flip this transaction to committed and assign a timestamp. And that's the timestamp we'll use to make it visible, because any read that comes in actually has to go check the timestamp and whether the transaction is committed or not. Right? Now that you've committed the transaction in a durable manner and every piece of data is replicated, we can now respond to the client to say, look, your transaction's good, it got committed, right? But the other thing to note here is every time a read comes in, you have to keep chasing back to the tablet leader, the transaction status table. So what we do is we asynchronously flush the timestamp value and the fact that this transaction got committed or aborted back to the tablet so they can be self-sufficient over time. Right? So before I go to the next thing, there's a couple of questions I just want to quickly address, and then we can go to the next one. The first one is Fabrizio says, awesome job, congrats, thank you. It's a very complex architecture, but any chance to turn it into a Postgres extension or something like that instead of maintaining a modified version? He believes there's a lot of cool things to contribute to Postgres. So, hey, Fabrizio, absolutely something we tried to do in the beginning, but here were a couple of things that are hard, right? Practically with this setup. The first one is that the system catalog of Postgres is also following the same kind of a setup. which means YugabyteDB system catalog is actually replicated and goes across nodes, whereas Postgres' system catalog is just a set of files, right? It just generates a set of files. So we've had to do a bunch of changes to the system catalog itself. So these are changes which are very much at the core of Postgres, and these are things, like I said, we are completely open database too, like fully Apache 2.0 and so on. So there's really no limitation to being able to contribute back to Postgres. However, it will change the architecture of Postgres quite a bit, and we just want to make sure that folks in the Postgres community are also okay with it. So we didn't want to spring a huge change like this without knowing what's coming down the line, right? So we'd love to collaborate with the Postgres community to see whatever we can contribute back. However, just want to call out that these changes are quite fundamental in some areas, right? So that's why we said we'll do the other track of actually rebasing to the latest version of Postgres, and we move our changes up to Postgres and maintain it in lockstep. But we are changing quite a bit of things under the hood. Okay. Livetus, I think, asks, can it tolerate any physical clock skew, even a catastrophic clock failure? Yeah, absolutely. I mean, yes, Livetus, like the way we do this is a clock failure is not a problem for us. That's usually not. We bound the clock skew, though, to a maximum allowed clock skew, right? So what we tell the users to do is to configure, like, if I read time on node 1 and time on node 2, what is the maximum synchronization guarantee that folks can give, right? Typically, with a reasonably configured NTP system, this is around 500 milliseconds. Now, we can work without that assumption too, because there's heartbeats flowing in the system every so many milliseconds anyway, and it normalizes time. But we do look for a max bound on the clock skew, whatever that is, right? Now, why do you need this, right? You could have in very large clusters, I'm talking about hundreds of nodes or 100 nodes or so, where you could have some islands of machines that don't frequently communicate with each other, right? So and so in these scenarios, you need to have some kind of bound on. If you look at a timestamp that says there's timestamp 1 on node 1 and timestamp 2 on node 2, how can you compare them? Like, at what point in the future is one of these nodes going to like how long do you have to wait before one node is ahead of the other? So we ask for a max clock skew bound, and in practice we will try to be as performant as possible and not rely on that. But if safety requires it, we will make sure we're safe and slow down the transaction to make sure we restart it or do stuff to establish a causal chain. So, okay, Augustine asks, are reads always from master? What if follower is geo closer to app or user in a globally distributed database? I think great point, Augustine. You can read from the follower. However, that's a stale read, right? That's it's not going to be a system of record read or a read as if it's like if you're just thinking about an RDBMS and you're reading and writing from an RDBMS versus if you have a replica for the RDBMS and you're reading and writing from there, you'll get stale reads from the replica, but you'll get the actual source of truth from the master in that sense. In YugabyteDB, the masters are distributed across all nodes. You can kind of control the policy on where the leaders are. So the reads are always served from the tablet leaders or the transaction status tablets, but you can perform follower reads from one of the followers. So the replica reads from one of the followers, and they'll be stale. The next thing I want to cover is also related to your question, which is asynchronous replication. So this is unique to Yugabyte in the sense, none of the other distributed SQL databases actually support async replication. And we said this is actually quite fundamental to RDBMS workloads, because if you think about like what is the non-cloud native version of scalable and DR the highest level of DR and scalability you can get, it'll look something like an Oracle rack or an Exadata two clusters. And with a golden gate sitting in the middle, right? Like, so that gives you the best of DR and the best of performance and scale in each of the data centers. So we wanted folks that are trying to run that to be able to get that kind of a setup in the cloud. So you can think of 2 YugabyteDB clusters supporting Postgres as the API in this case, synchronous replication inside the cluster, and asynchronous across, right? So that is called X-cluster or cross-cluster replication. It allows 2 or more decoupled YugabyteDB clusters to consume the data changed either from one or the other, so both ways. Right? So this is effectively a way for us to capture the changes and send it to the other side and apply. So here's a few guarantees we'll go through real quickly. So the asynchronous replication guarantees in-order delivery of updates to a particular row or a tablet, right? And it applies mainly to non-distributed transactions. Ordering of transactions across tablets are not guaranteed. So you do transaction 1 on one tablet and transaction 2 on another tablet, and you first do transaction 1, then followed by transaction 2. We don't guarantee ordering in time because the hybrid logical clock and time normalization is not done across 2 different clusters. Right? And we believe this is a good enough trade-off where we don't need to maintain the causal order of transactions in the first cluster as it's applied to the second. Right? The second thing that's guaranteed is at least once delivery of changes. So that means you won't lose any update, and it's a monotonic set of updates, so you won't travel back in time. So these two together kind of get you your replication pipe to always move forward and to make sure you get every update. So the monotonic update simply says you don't travel back in time. And finally, we send periodic no-op records even if there are no writes on one of the clusters to make sure that in the source cluster to know that the sink or the destination cluster actually knows that it's caught up to what timestamp. If you look at transactions and conflict resolution, the way we do this on the sink or the destination is the last writer wins. So you could have a scenario where you have 2 clusters, A and B, and you write something on cluster A, and at the same time you write it on cluster B as well. And now A replicates to B, you get like possibly a conflicting write, right? The way that is handled is the timestamp. The transaction with the higher timestamp will win, and these times are independently issued by the 2 clusters on the 2 sides. The other caveat, and this is kind of standard to most RDBMSs, is the fact that if you have a constraint violation, you have a unique constraint or something on both the source and the sink, and you can simultaneously write to source and sink, and you can violate that constraint because each of the clusters sees that the unique constraint is satisfied. But when you replicate data, the unique constraint could get violated, so the transaction apply will fail. So what we recommend is don't do such things in the application tier. The conflicting updates will simply get dropped, right? So, and we originally thought about exposing conflict resolution to users. Again, this is something we can do in the future, but we said it's just too complicated to use, and we didn't find enough real use cases to guide us to build this. So at this point of time, we're just doing last writer wins, right? And we are working on distributed atomicity in the sense right now, the transactions that are applied in the source cluster, each of their individual row updates go with the same timestamp, but they're not applied atomically in the destination cluster. So what we are planning to work on is to put all of these transactions, all of the operations inside a transaction in a waiting to commit state on the destination cluster, and to make it atomically visible, right? So it's just like making the transactional but asynchronous replication guarantee stronger and stronger. Okay, so there's the last one is obviously in progress, right? So so the way this works is you can have a universe or a cluster on the left, which is the source, and you can have another cluster with a different set of nodes and different machine types on the right, which is the destination. And you can unidirectionally replicate data from the source to the sink. And you can do bidirectional replication by setting this up 2 ways, right? From A to B and from B to A, and you're going to get what you would call a multi-master setup or a bidirectional replication setup. So that's mostly the 7 steps that we talked about, and all the way from, should we pick the Postgres code base? Is it going to be too complicated? To how do we map the set of steps going from, Postgres to Spanner, and how do we triangulate that to, all of the details around achieving scale and high availability and distributed transactions and all of those type of concerns, to finally, what do we do when it comes to asynchronous replication on top of 2 clusters where data is synchronously replicated, right? So that's overall the set of things that we put together, and all of this is in the open source. And like Fabrizio asked, and I had responded, we'd love to contribute this back to Postgres, some part of this, but it is fundamental in terms of the architecture and the places it touches. And a lot of places we've had to change the way, for example, the query plan works also. I mean, it's probably a talk of its own, where we can talk about how we regroup data and how we actually change the execution plan for some of the transactions or operations that we do in a distributed database, including a lot of tricks to minimize the effect of network latency. But we are a fast-growing open source project, so if what you guys heard is interesting, then come join our join our community Slack. We have a lot of interesting discussions going on about distributed systems, RDBMSs, cloud native, etc., etc. It's fully open source, so you can just download and try it on your own, and give us a star while you're at it. So I'll pause here to see if folks have questions, right? And we can go from there. Other questions, folks? Okay, so I think Augustine has a question on what happens on async replication failure, right? Yeah, great question. So the high-level answer is that let's define what a failure means, right? So when you're replicating asynchronously from cluster A to cluster B, you could have a network partition which kind of stops your asynchronous replication from happening, right? That's the scenario I'm guessing you're referring to. What would happen is the updates would start queuing on cluster A, right? And once the network partition heals, cluster A would start sending all of those updates to cluster B, right, in a batched fashion. Now, you could have the partition happen for a very long period of time, right? In which case, you'd be piling up so many updates that after a certain point, you're never going to be able to catch up, or you're going to run out of space, right? So the way this works on the source clusters, you can actually configure the length of time and the size of data. You can do configurations based on both to figure out how much of a partition tolerance do you want to have, right? You can say, I want to tolerate a day or 2 days or 7 days or just an hour or whatever it is, right? So if the amount of retention on the source cluster is exhausted, like because you either hit the space threshold or you hit the time to replicate, like that window threshold, because your partition existed for many days, then your system actually, the replication link fails, and you have to rebootstrap your destination cluster, which is B, from the source, and kind of think of it as a distributed backup restore, and then start the replication asynchronously again, right? But this is in the double catastrophic case when you both the replication link fails and it fails for so long that you're not able to do the retention on the source cluster. Typically, we'd expect the retention on the source cluster to be sufficient and the replication link to heal within time, and you'd be able to push the updates in time. Hopefully that answered the question. Sure, welcome, Augustine. Other questions, folks? Like I said, give it a go, guys. I think, and let us know what you think. There's a coverage. It's still not 100% coverage on PostgreSQL. I'd say it's about 70-75% coverage, but we do support a lot of the advanced features also, like stored procedures, triggers. We also support a bunch of extensions. Like, for example, we started putting some default enabled and default included extensions into YugabyteDB, like PG stat statement, which is universally always running now, or even things like PG crypto or PG audit. So there's a whole bunch of extensions that we support, like the query layer extensions, as well as like most of the functionality, right? So like there are the things that we're working on right now in terms of PostgreSQL coverage are things like GIN indexes and text search, gist indexes and geospatial. So we're trying to put coverage for those type of things. But most of the other things should just work, right? So give it a spin, let us know, and join our Slack community. Would love to hear from you folks.